Hey guys, so today we're going to talk about the utility function, why it can't ever decrease. We're going to look at an example. We're going to define marginal rate of substitution and derive it for the Cobb-Douglas case, and look at three different graphs, where it's a curve like in the Cobb-Douglas case, where the indifference curves are perfect substituted goods and they'll be straight, and spoiler, where they're complements and they'll be L-shaped. So utility is defined as the happiness or satisfaction that you get from something. It's not like paying your utility bill, which you don't get satisfaction from. Obviously, we can't measure happiness, but we can try if you're an economist and we put a number to it, right? So with a basic example like food, right? You would think that at some point, if you keep eating, it would fall off, right? You would get less satisfaction, right? This is utility, as you eat something, right? Food. But that's not the case. In reality, or not in reality, in economics, utility never falls off. It can only stop increasing quickly, but it can never decrease, right? This can never happen. It can never have a peak. And the best example, I think, is with money, right? And the utility curve of money, now let's write money, is logarithmic, right? It goes like this. Why does this make sense? You would think the more money you have, the happier you would be. But no, you'd be wrong. Many economists, myself including, argue that utility of money, let's just write that, is logarithmic, right? Why is that? If I gave you $100, you'd be happy, right? You'd be like right here, you'd be like, wow, $100, that's so cool. If I gave you $1 million, you'd be just bouncing off the walls ecstatic, right? You'd be like, wow, $1 million, you'd be up here. Way more utility. But if I gave you $1 billion, you're not going to be 1,000 times happier than with $1 million, right? You'd be somewhere over here. And the difference between $1 million and $1 billion would be much smaller than the difference between 100 and 1 million. Think about it. You're not going to be 1,000 times happier. How can you express happiness 1,000 times more of something, right? You're already going to be like crazy about 1 million. You're not going to be 1,000 times crazier about 1 billion. So that's why it's logarithmic. But you're never going to be sadder, right? You're not going to start becoming sad if I give you $10 billion. That's not going to happen. You're just going to be less happy. So you can't have this. You can't have decreasing utility. Let's take a look at an example. So let's say your utility function of two variables, some variables x and y, looks like this, right? Whatever the variables you want. And we have two cases. So the first case, utility of 1, will say 7 and 7. So you have 7 and 7 of the two variables, x and y. Obviously, this is square root of 49 or 7, right? And utility 2, our two variables will be equal, let's say, 16 and 4. And that is the square root of 16 times 4 is 64, or 8. So obviously, this will make you happier, this combination. Even though it may seem strange, why would 16 and 4 be better? 7 and 7 seems more balanced, right? Maybe you'd be happier, but you'd be wrong. In this function, maybe if you had a different utility function, 7 and 7 would make more sense. But in this case, we look at the higher number, right? We put a value to your happiness, which may sound weird, but that's what economists do. We measure everything. So yeah, you'd be happier with 8. So the utility function is used to construct indifference curves, which is something I'm sure you've heard of if you're studying microeconomics. And as the name implies, an indifference curve is a curve along which you are indifferent, right? So if you have the two variables y and x, and you have some line, a curve usually, then you would be equally happy along any point on this line, right? It doesn't matter what the combination is. The utility, the number that you get here, will be the same. That's why you're indifferent to the combination. Whatever you get. For example, we can switch 4 and 16, 16 and 4. You're still going to get 8, right? That's what this implies, that whatever combination you choose, you're going to be equally happy. Now, how is the indifference curve constructed? Well, it's defined as the marginal rate of substitution at any point is the slope. And the marginal rate of substitution, MRS, is defined as marginal utility of x divided by marginal utility of y. And this pretty much means the ratio that an agent is willing to switch one good for another, how much they're willing to consume one good in relation to another. So let's start building these up. Let's do an example. So we have the famous Cobb-Douglas function, right? You can check out the video we did on that below. But before we did production, now we can do utility with Cobb-Douglas. Why not? So we have utility, once again, of xy. And if you remember, the function is x alpha, y 1 minus alpha, right? Cobb-Douglas. Can't live without him. Without them, rather. So let's do mux and muy. So that's the derivative with respect to x and respect to y. So let's set it up. We have marginal utility of x is equal to the derivative of this thing, right, of u. So that is alpha, x to the alpha minus 1, y to the 1 minus alpha, or alpha, x over y, alpha minus 1. Does that make sense? Because we can just take y to the minus 1 power. This will switch to alpha minus 1, and then we can make it as one fraction. And then let's do the same for marginal utility of y. Now it's d over dy, right? Because we're taking the derivative with respect to y of the function u. And what do we have? We have 1 minus alpha, x to the alpha, we don't touch it, and y to the 1 minus alpha minus 1 is minus alpha. And this simplifies to 1 minus alpha, and just like before, x over y to the alpha. Does that make sense? Because we're minus alpha over here, it's the same as 1 over y to the alpha. So we just put it all into one fraction. So then in this case, for Cobb-Douglas, the slope of the indifference curve will be this thing divided by this thing. Or, let's do it. Yeah, I can do it over here. MRS sometimes you'll see it xy like this. Sometimes you won't. It's the same thing. Well, let's just include it for reference. Is equal to this mess, alpha of x over y, alpha minus 1, divided by 1 minus alpha, x over y to the alpha. Now this looks crazy, but it's not. We can simplify it. So we have alpha over 1 minus alpha. Now how would we simplify this? We have x over y, alpha minus 1 minus alpha is minus 1, or alpha over 1 minus alpha, y over x. So this whole mess simplifies to this, which is pretty simple. And just like before, this is actually the Cobb-Douglas indifference curve. Surprise! That's what I drew. Obviously, let's just draw it again. Because this is a contour map, right? This is two variables. We draw it like this because there's many lines. It's not just one line, right? This is actually something that confused me, so let me just take a tangent real quick. Before, we would write f of x equals y equals something, right? And it would just be a graph like this. And when you get into multivariate calculus, z equals f of x, y equals something. And this would be a three-dimensional function, right? I'm sure you've seen graphs where it's like this, right? Where you have z, you have x, and you have y. But this is not the case. This is something called a contour map or a contour plot, where we use the two variables side by side. We don't assign a third variable, the z variable, to show height or anything. We just draw it like this, right? Obviously, then you would have these three curves, the indifference curve 3, indifference curve 2, and indifference curve 1, and you want to be as high as possible, right? So you would prefer to be anywhere on the third curve because it gives you diagonally a higher value, right? And this is the Cobb-Douglas indifference curve. Then you have a couple more interesting ones. When you have a situation where all the lines are parallel to each other, this is something called perfect substitution. This means that you have goods that can be, surprise, perfectly substituted. My favorite example is something like Pepsi or Coke, right? When you go to the store, at least for most people, you don't really care which brand of something you're going to get. If they don't have your favorite apple juice, you're just going to get the second brand of apple juice. You're not going to go to a different store just to look for that particular brand of apple juice. These things are perfectly substitutable, right? And in that case, you don't have curves, you have straight lines. And the third example is when you have perfect complements, right? So this is subs. And perfect complements, surprise, are L-shaped. What is a perfect complement? These are goods that go with each other and with nothing else, like left and right shoes. If you have two right shoes, you're not going to be just as happy if you have a right shoe and a left shoe. Complements they complement each other. You can't go without them. Another less extreme example is like hot dog buns and hot dogs. If you have 10 hot dog buns and 0 hot dogs, you're not going to be as happy as if you have 5 hot dog buns and 5 hot dogs. So if before, in these cases, you don't really care where you are on the line at which point, with perfect complements, you do care, because you only want to be right where they meet, because this is when you have left shoe, right shoe. If you anywhere up here, you can have great 3 right shoes but 0 left shoes. That doesn't make any sense. You don't want to be there. So in this case, you only want to be on these points. And just like before, you want to be higher up. So you always want to be as high up diagonally as you can be. So once again, if this is I3, you want to be on I3 because you have 3 pairs of shoes instead of just 1 pair like down here. You're happier with it. Want to learn more? Check out the next video. Quick reminder to subscribe to GeeklyEDU.